Many situations arise in statistics where we want to combine independent, normally distributed random variables. This comes up when we're, for instance, generating a sampling distribution for a sample mean, which is the basis for inference about population means. So it's a very important topic. The important thing to remember is that any linear combination of independent normal random variables is also a random variable. You can find its mean and its standard deviation using the rules for means and variances, and then you can calculate probabilities pertaining to that combined variable using what you know about standard normal distributions. So here's an example. Clyde and Earl are pro basketball players. Clyde scores, which we're going to abbreviate with C, are normally distributed with a mean of 22 points and a standard deviation of 5 points. Earl's scores, which we'll abbreviate with the capital letter E, are normally distributed with a mean of 18 points and a standard deviation of 4 points. If Clyde's and Earl's scores are independent, what is the probability that in a randomly selected game their total score is greater than 45 points? Well, when you get a problem like this, the first thing you have to do is define a random variable that you can use to solve this problem. Since you're being asked a question about the total score, it would make sense to define that variable as the total score, which is just the sum of C plus E. You can find the mean of that variable by using the rules for means. The mean of T is equal to the mean of C plus the mean of E, which is 22 plus 18 equals 40. And you can find the standard deviation using the rules for variances. The variance of T is equal to the variance of C plus the variance of E, which is 5 squared plus 4 squared. 25 plus 16 is 41. And then the standard deviation of T is the square root of 41, which is about 6.4. So this is really the only thing that's new. After this, what we're going to do is basically a standard normal calculation following the steps that we've already looked at. So what we want to do is state the probability we're looking for in terms of the combined variable. In this case, we're looking for the probability that T is greater than 45. Here's a sketch that illustrates that. You notice I have on my axis a label. I drew in the normal curve. I put my mean in, and I put the boundary value of 45, and I shaded to the right of that. That's really all you need on a graph like this. A label on your axis, a value for the mean, a value for the boundary value, and the appropriate area shaded under the curve. Now we're going to standardize this expression from up here. And the way we do that is we subtract the mean and divide by the standard deviation on both sides. So over here we're going to subtract mu t divided by sigma t. Over here we're going to subtract 40 and divide by the square root of 41. And that simplifies down to the probability that z is greater than 0.7809. And we can solve for that using our calculator. If you go to normal CDF and put this in as your left bound and put a big number like 999 in as your right bound, you will get 0.2174 for the probability we're looking for. And then you write a conclusion. The probability that in a randomly selected game, Clyde's and Earl's total score is greater than 45 points is about 0.2174. So basically everything from here on down is stuff that you've already seen in the context of solving problems involving normal distributions. The only thing that's new is defining a new random variable that's a linear combination of other random variables that you already have, and then using your rules for means and variances rather to find the mean and the variance and standard deviation of the new variable. And then after that, it's the same old stuff. Here is another example involving the same two players, Earl and Clyde. And just to remind you, Clyde's scores are normally distributed with a mean of 22 and a standard deviation of 5. And Earl's scores are normally distributed with a standard deviation of 8, rather a mean of 18 and a standard deviation of 4. And what we're looking for here is the probability that Earl outscores Clyde. Now if you just translate that into statistics, into math language, it would look like this. We're looking for the probability that E is greater than C. This is not very useful to us, however, because we have two random variables in this expression, and we can't calculate this probability using the methods that we know. So what we have to do is turn this into an expression that has just one random variable in it. And one way you could do it is just to subtract c from both sides in that inequality and rewrite it like this. The probability that e minus c is greater than 0. And in this case, this e minus c could be combined into one random variable, and then we'd have one random variable inside this expression, and we'd be in business. So we're going to define this variable as e minus c, and I'll call it d because it's a difference. And the mean of d, mu d, is just the mean of e minus the mean of c, and that's going to be 18 minus 22, which is negative 4. The standard deviation of d is the square root of the sum of the variance of the sum of the variances. We have the variance of c is 5 squared, the variance of e is 4 squared. That's 25 plus 16, or 41. And that's the same as before when we were working with the problem with total. That was the the variance of a difference and the variance of a total are the same thing. So the variance of a sum, the variance of a difference, they're the same. So it's not a surprise that you get the square root of 41 for this standard deviation. Now the probability we're looking for is the probability that d is greater than 0. Here's a beginning of a sketch. I have my normal curve and I have my axis. My axis needs a label, so I'll put d on there. My axis needs a mean marked. Well, the mean is negative 4. And I need to put a boundary value in. Well, let's see. We're looking for the probability that d is greater than 0, and 0 is to the right of negative 4. So we'll go out here to the right. And that'll be 0, and then we'll mark this probability over here. So that's what we're looking for, is this area over here. That probability is basically right there on the picture. And then we're going to standardize that expression. We're going to take the probability of d minus the mean of d divided by the standard deviation of d is greater than 0 minus negative 4 over square root of 41. And that is approximately the probability that z is greater than 0.6247 when I simplify that. And then I go to my calculator and I find that this is approximately 0.2661. And then I write my conclusion. The probability that Earl outscores Clyde in a randomly selected game is about 0.2661. And there you go. So most of this stuff is old. Like everything from about here on down is stuff that you've done before many times. The new stuff is up here, where you have to define a new variable, find its mean and standard deviation, and then the rest is what you already know.